I welcome the audience. My name is Károly Kubicsko from Eötvös University. In my lecture, I will speak about the hydrolysis of N N-dimethylindole-3 ethylaminium cation, the oxidized form of the endogenous psychedelic N N-dimethyltryptamine. Okay. First, I would like to briefly summarize what will be discussed in the lecture. I will speak about the applied methods and present the chemical reaction of interest. For this followed by the discussion and summary of our findings. Within the framework of Born-Oppenheimer approximation, the motion of electrons and nuclei can be separated. The electronic and nuclear Schrödinger equations can be solved independently. In our work, we focus on equation 2, the electronic Schrödinger equation. All computations were performed using the Gaussian C1 program package. The examined systems contains 31 to 37 atoms. At first, we wanted to use ab initio methods, but we found them extremely time-consuming. Therefore, the DFT approach was our choice to be accurate and computationally affordable. The M062X OCCPVDZ level was used for geometry optimizations and frequency calculations, as well as the thermochemical analysis. The M062X OCCPQZ level has been applied for single point energy calculations. The best available integration grid was chosen in all calculations. In order to take account of the solvent effects, we used the SMD variation of IEF-PCM implicit solvent method. The total Gibbs-free energies were computed as shown in equation 4. The Gibbs-free energy corrections determined at 36 centigrades and atmospheric pressure in order to simulate the environment of the body. The activation barriers and the reaction rate constants are connected. The connection between them is described by the equation 5. Knowing the activation barriers, the corresponding reaction rate constant can be calculated. The lowest rate constant corresponding the highest activation barrier, which is the rate determining step of the reaction. In this figure, the metabolism processes of three biogenic amines are presented. In the first row, the tryptamine, the second row, and the N-methyltryptamine, and the third row is the N N-dimethyltryptamine. The first step of the metabolism process is the oxidation by monoamine oxidase. During the enzymatic reaction, the cofactor of MAO is reduced to Z H minus, and the amines oxidized to iminium cations. It is followed by the hydrolysis of the iminium cations, which results in indole-3 acetaldehyde and the corresponding amine. The final step is the oxidation of the aldehyde by the aldehyde oxidase or the aldehyde dehydrogenase enzymes, and the product is the indole-3 acetic acid, as known the auxin hormone, which is the main growth hormone in plants. I labeled the examined reaction by the red rectangle. This figure, the schematic figure, shows the hydrolysis of a general iminium cation with hydroxidion. In our case, the R group corresponds to methylindole group, and Q and Q prime are methyl groups. The first step is the addition of hydroxide anion to the imidocarbon. This step is followed by an intramolecular proton transfer from the oxygen to nitrogen. The last step is the cleavage of the C-N bond, and therefore aldehyde and secondary amines are produced. The examined reaction contains the EMDMT plus cation and one hydroxidion with 0, 1, and 2 additional water molecules, as can be seen on the figures. The whole reaction contains 4 elementary reaction steps. The first is the addition of hydroxidion on the carbon atom. It is followed by the inversion of nitrogen. This is necessary because after the addition of hydroxidion, the lone pair of the nitrogen and the hydrogen of the hydroxyl group is on the opposite they have opposite spatial orientation. Therefore, after the inversion of the lone pair, the possibility to form a hydrogen bond between them is possible. We found that the rate determining step of the reaction is a concerted proton transfer from the hydroxyl oxygen to the nitrogen. This figure shows that the effect of the additional water molecules, the highest TS3 activation, TS3 transition state corresponds to the determining step, and with 1 and 2 additional water, the height of this barrier can be reduced. On this figure, I presented the structure of the transition state in the R0 reaction with just the hydroxydion and the iminium cation. A four-membered transition state, four-membered ring has in the transition state, and by applying 1 or 2 additional waters, this structure, this four-membered structure, is extend to 6-membered or 8-membered rings, and this geometrical this enables a geometric relaxation of the structures. So in our study, we found that the concerted proton transfer process is the rate determining step. By applying additional water molecules, the activation barrier significantly reduced with 1 water, and with applying another water, it can be reduced further. Thank you very much for your attention.
Thank you very much. Any questions? I'm assuming you do your calculations with some kind of density function, right?
Yeah.
So do you use some available package like the VMA package or also the package, or do you have some own development?
We just use the Gaussian 16 program package in our work. This was the only software. Please.
If are not like, I will think about it. You are adding 1 or 2 additional waters to reduce the energy boundary between the transition states. It's just this geometrical structure that helps in the relaxation of the molecule, and it's not a bond. It's not a ionic bond. It's not a covalent bond. What are the interactions that are like? What are the ones yeah, like there.
Yes. So the water molecules form a hydrogen bond between the hydroxyl group of the intermediate, and by this hydrogen bond, the proton can be transferred more easily. So
That was my question. Hydrogen bond.
okay, so can you repeat the question?
No, it was if I wanted to know if it was like I don't know, van der Waals or like
Yeah,
it was a nitrogen bond.
Hydrogen bond.
Okay, any further questions or remarks? If there's no, let's thank Farai again.
Thank you.